Hello everyone and welcome back. In today's video, we are going to be covering another topic of probability, which is another type of special probability distribution called a binomial distribution. So binomial experiments are special types of probability experiments. So there are many types of probability experiments that only have two outcomes, success and failure. So for example, if you make a free throw, there's only two outcomes. You're either going to make the throw, which is a success, or you're going to miss, which is a failure. Now, probability experiments like these that only have two outcomes are called binomial experiments. So a binomial experiment is a probability experiment, and it has a bunch of conditions that it does need to meet in order for a probability experiment to be considered a binomial experiment. So the first condition that must be met in order for it to be a binomial experiment is that the experiment must have a fixed number of trials, and each trial is independent of the other trials. That is actually extremely important. So the occurrence or outcome of one trial does not affect the occurrence or outcome of any of the other trials. So whether or not one trial succeeds does not affect whether the next trial fails or succeeds. Another condition of a binomial experiment is that there are only two possible outcomes that are of interest, either success or failure. And in each binomial experiment, success will be defined as something. So success is could be making the free throw. So success will be defined as something, and then the alternative is failure. And there are only two outcomes, success and failure. The third criteria for a binomial experiment is that the probability of success is the same for each trial. So probability of success is not going to change from one trial to the other. It is always going to be the same for every single trial. And then the random variable x will count the number of successful trials. So the random variable x in this case is going to be the number of successes. And there's going to be a lot of variables that are used in binomial experiments, and it is noting what stands for what. So n is actually going to stand for the number of trials. The probability of success for a single trial is going to be denoted by the variable p. And I am going to make a note that p is going to be a decimal or a fraction. Do not use p as a percent. Now, since there's only two outcomes, success or failure, we denote the probability of failure by another variable called q. Q is also either a fraction or a decimal, not a percent. And if you are not expressly given q, it is easy to find q. It is just 1 minus p, the probability of success. Since there's only two outcomes and the probability of the two outcomes need to add up to 1, to find the probability of failure q, you just do 1 minus p. And then x is the random variable that counts the number of successes. So the smallest that x could be is 0. That means none of the trials are successful. X could take on a value of 1, 2, all the way up to n, which means that all of the trials would be successful. So x will be some number of successes between 0 and n, the number of trials. So what we're going to do for each of these is we're going to determine whether the experiment fits the criteria for a binomial experiment. And if it does, we're going to figure out the values of n, p, and q, and we're going to list all of the possible values of the random variable x. And if the experiment does not fit the criteria for a binomial experiment, we're going to explain why and what condition it failed. So for this first one, a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So let's go through the binomial experiment criteria and see if this fits. So criteria number 1, the experiment has a fixed number of trials. Yes, there's a fixed number of trials, there's 8 patients. And each trial is independent of the other trials. So does the success or failure of a surgery on one patient affect the success or failure of the same surgery on a completely different patient? It does not. If they're different patients, they are independent trials, and whether the surgery succeeds or fails for one patient doesn't affect the success rate for the surgery on another patient. So all of the trials are independent. And there are only two possible outcomes, success or failure. Well, this surgical procedure is either going to succeed or it's going to fail. So since there's only two outcomes, success or failure, it does fit the second condition to be a binomial experiment. Criteria number 3 is that the probability of success is the same for each trial. So the surgery has an 85% chance of success for every single patient. So this is just a blanket 85% success rate for the surgical procedure in general. So that means that for each of these patients, the probability of success is the same, that 85%. So yes, the probability is the same for each trial. And then the random variable will be the number of successful trials. So successful surgeries. So this does fit the criteria for a binomial experiment. So this is a binomial experiment. So what we're going to do then is we are going to list the values of n, p, q, and then list all of the possible values of the random variable x. So let's start with n. N is the number of trials, so there are 8 patients. Sorry. And n is going to be equal to 8. P is the probability of success as a decimal. Well, this has an 85% chance of success, so as a decimal, P is 0.85. Q is the probability of failure, and if you don't, since we're not given Q, we need to find Q. So Q, probability of failure, is going to be 1 minus the probability of success, gives us a probability of failure Q to be 0.15. And x is the number of successes. So the smallest value that x could take on would be 0, which means none of the surgeries are successful. Another value x could take is 1, meaning exactly 1 out of the 8 surgeries is successful. X could take on a value of 2, meaning exactly 2 out of the 8 are successful. A value of 3 would mean exactly 3 of the 8 surgeries are successful. 4, 5, 6, 7. And then the last option is that all 8 of the surgeries are successful. So those are all of the possible values for the random variable x, which counts the number of successes. All right, so for number 2, a jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. That's actually going to be important in a few minutes. The random variable represents the number of red marbles. So here's the thing about binomial experiments. It does look at first glance like there's more than 2 outcomes. We have red, blue, and green. As long as success is defined as something and failure is defined as everything else, it could still fit the criteria for a binomial experiment. In this case, success is defined as red marbles, and that implies that failure is anything that's not red. So there are still only 2 outcomes here. Success, red marble; failure, any other color. However, you're going to find that this is not a binomial experiment because the marbles are drawn without replacement. So the probability of success for the first trial is going to be different than the probability of success for the next trial, because as soon as you remove that marble from the jar, you have changed the sample space. You have changed the sample space. It has gone down by 1. And as you remember from conditional probability, remember when we drew cards without replacement, it changed the probability of the next card. The same thing's going to happen here. So the act of drawing that first marble and not replacing it is automatically going to change the probabilities for drawing any of the other marbles. So these trials are not independent. These trials are dependent events. Because the trials are not independent and the probability of success is not the same for each trial, this is not a binomial experiment. Even though success was defined as red and failure was defined as everything else, because the trials are not independent with that not replacing, the probability of success changes for each trial, and that makes it not a binomial experiment. Now, to find the probability of exactly X number of successes, we can do this in 2 different ways. We can use what is called the binomial probability formula, or we can use a graphing calculator. And I will say I'm going to introduce the binomial probability formula so you see it, you work with it, you know what it is and how it works. And then for any other binomial probabilities, you're going to be allowed to use a calculator. I will have calculator steps a little bit later in this video. So this is going to be the probability of X number of successes in a binomial experiment, and it is given by this formula. Now, if you've never seen these exclamation points before, these are called factorials. Factorials are a specific type of mathematical operation involving multiplication. So what a factorial is it is that number times all of the integers that came before it all the way down to 1. So for example, 5 factorial. 5 factorial can be expanded out as 5 times 4 times 3 times 2 times 1. So that's what those are. So the probability of X number of successes in a binomial experiment is n factorial divided by parentheses n minus x factorial times x factorial times p to the power x times q to the power of n minus x, which remember, if x is the number of successes, n minus x will be the number of failures. So we're going to do one example where we're going to use the binomial probability formula, and then for here on out for the rest of this video and all of your homework and all of your exam questions, you can go ahead and use a graphing calculator. I'm not going to force you to do the binomial probability formula for every single one. You can use a graphing calculator after this example. All right, so rotator cuff surgery has a 90% chance of success. The surgery is performed on 3 patients. We're going to find the probability of the surgery being successful on exactly 2 patients. So since this problem is pretty much almost exactly like, this first example here, this is a binomial experiment. It fits all of the criteria. So let's first identify all of our variables. So this 90% chance of success, that is going to be our p-value as a decimal. So p is 0.90. The surgery is performed on 3 patients, so n is equal to 3. We're going to find the probability of the surgery being successful on exactly 2 patients. So we're finding the probability of exactly 2 successes. Another thing we need really quick is the probability of failure Q. So 1 minus 0.90 is 0.10, so there's a 10% chance of failure. So the probability of exactly 2 successes is going to be given by this formula here. So it is going to be given by n factorial, so it is going to be given by 3 factorial, divided by 3 minus 2 factorial, times 2 factorial, times p to the power x, so 0.90 to the power 2, times q, 0.10, to the power of n minus x, so 3 minus 2 is 1. All right, and then expanding this out, remember 3 factorial is 3 times 2 times 1. 3 minus 2 is 1. 1 factorial is just 1. Times 2 factorial, which is 2 times 1. Times 0.9 squared times 0.1 squared. Sorry for the amount of glitching. Sorry, 0.1 to the first power. Sorry for the amount of glitching that's going on. All right, so 2 divided by 2 is 1. That is a common factor. So if you just do 3 times 0.9 squared times 0.1, you get a probability of 0.243. So there is only a 24.3% chance that this surgery is successful on exactly 2 patients. It didn't say at least 2 or less than 2. It just said find the probability that it's successful on exactly 2 patients. So that's 24.3%. So you're going to find that the binomial probability formula or the steps in the graphing calculator will only give you the probability of exactly X successes. These calculator steps or formula are not going to give you the probability of at least X successes or less than X successes. It's just going to give you the probability of exactly X number of successes. So to find binomial probabilities on a TI-83 or TI-84, you're going to be using these steps. And it's going to be the same deal where I can't if I try to show you this in the same video with this running, I'm going to crash the PC. So I have gone ahead and pre-recorded a video that walks you through all of these steps of how to find binomial probabilities on a TI-84 or TI-83, and I'm going to leave a link to that video in the description. So let's say that the results of a recent survey indicate that 67% of U.S. adults consider AC a necessity. You randomly select 100 adults, and you're going to find the probability that exactly 75 of them consider AC a necessity. So we're going to use a calculator to find this. So just really quick, going through the criteria for a binomial experiment, there's a fixed number of trials, there's a fixed number of respondents. Each respondent is independent of the other. So whether one person says that AC is a necessity or not does not affect whether the next person you ask says AC is a necessity. As long as you don't do anything that will make them bias, each respondent is going to be independent of all the others. There's only two possible outcomes. Success is defined as a necessity. So success is defined as them saying that AC is a necessity, which means failure is defined as AC is not a necessity. So there's only two outcomes. It's either necessary or it's not. It's either success or it's failure. And then the probability of success is going to be the same for each trial because the results indicate that 67% of adults consider AC a necessity. So P is going to be the same for each trial. P is going to be 0.67. So that means that N, which is the number of trials, is going to be 100. And then X is the number of successes. So we are finding the probability that exactly 75 of them say, yes, AC is a necessity. So X is going to be 75. Now the thing with these graphing calculator steps is you do not need to find Q. It will figure out Q for you. So all you need are the values of N, P, and X. Now I will say that the TI-84 does have a menu that you can enter all of these in. The TI-83 does not. So whether you have a TI-84 or a TI-83, eventually you will go back to your home screen and you will see this binom PDF, and you're going to enter the values of N, P, and X with commas in between them in that order. So you will eventually get to a screen that says 100, comma, 0.67, comma, 75. So N goes first, P goes second, and then X goes last in that order with commas between them. So on your graphing calculator, you should get a probability of approximately 0.02. So there's about a 2% chance that exactly 75 of them consider AC a necessity. Now, finding binomial probabilities on a graphing calculator is nice and easy and fast. So we are going to be using a graphing calculator pretty much exclusively. So when you're constructing a binomial distribution, especially, you're going to be finding a ton of binomial probabilities, and you're not going to want to waste your time using the binomial probability formula for each one. So let's say that in a survey, adults are asked to identify which devices they use to access social media, and the results are shown in this table. Now, 7 of those participants were randomly selected and asked whether they use a cell phone to access social media. And we're going to construct a binomial probability distribution for the number of people who said yes. So a binomial distribution is the same as the discrete probability distributions that we covered in the last video. In a binomial distribution, it is going to be a list of all of the possible values of x together with their corresponding probabilities. So it is going to be all of the possible numbers of successes listed together with their corresponding probabilities. Now, success in this case is defined as using a cell phone, which means failure is defined as not using a cell phone. So success is using the cell phone. That means failure is not using a cell phone. So failure would be any of these other categories. So, since 46% of the respondents say that they use a cell phone to access social media, that means the probability of success is 0.46. N is the number of respondents that you selected. So you selected 7 of them, so N is equal to 7. And X is going to be the number of successes. So the number of successes, the smallest it could be is 0. There could be 1 success, 2 success, all the way up to 7. So what I'm going to do is I'm going to make a 2-column chart, X in one column and the probability of X in the second column. And under the X column, I'm going to list all of the possible values of X, all of the possible number of successes. So the smallest X could be is 0, which means 0 out of those 7 say they use a cell phone. Another value that X could take is 1, which means exactly 1 out of the 7 said they use a cell phone. X could be 2, which means exactly 2 out of the 7 say yes, they use a cell phone. Exactly 3 successes, 4, 5, 6, and then another alternative is 7, which means that all 7 of those people that you ask say that they use a cell phone for accessing social media. And then what we're going to do is we're going to use a graphing calculator to find the probabilities of each of these numbers of successes. So we're going to start with the probability of 0. So the probability of 0 successes, that is going to be using the Binom PDF option. And then your N is going to be 7, your P is going to be 0.46, and your X is going to be 0. And then when you do that on a graphing calculator, you should get a probability of 0.0134. Now, a quick shortcut that you can use to avoid having to go through the entire menu all over again is if you, on your calculators, press second enter. What that will do is if you press second enter on your calculator, you will notice that your calculator's input is now exactly the input that you just did. So it'll give you that Binom PDF 7, 0.46, 0. Now, the only thing that is changing for each of these probabilities is that last number, X. So if you're going to find the probability of 1 success, all you need to do is take that existing input, leave the 7 alone, leave the 0.46 alone, and all you're going to do is you're going to change that last number 0 to a 1. So you just use your arrow keys to kind of scroll around, and you're going to delete that 0 and replace it with a 1. And then if you press enter again, it'll do that binomial probability with exactly 1 success, and you should get a probability of 0.0798. And then you can keep doing this for each of them. So if we press second enter again and you replace that last number 1 with a 2, you will get the probability of exactly 2 successes. So your calculator will eventually look like this. It'll be the Binom PDF, which with a 7, 0.46, 2. And the probability of exactly 2 successes should come out to 0.2040. I'm going to give you the rest of the binomial probabilities. If you want to pause the video and work through these and then resume to check your answer, please feel free to. So the probability of exactly 3 successes, so just replace that last number with a 3, will be 0.2897. Probability of exactly 4 successes is 0.2468. Probability of exactly 5 successes is 0.1261. Probability of exactly 6 successes is 0.0358. And this last one is going to be, your calculator might put in scientific notation, it might not, is 0.0044. So this list of all of the possible values of X, all of the possible numbers of successes listed together with their corresponding probabilities, this is called a binomial distribution. It's a probability distribution specifically with binomial experiments. So for this next one, we're going to be using some binomial probabilities again, but remember, whether you're using the formula or you're using a graphing calculator, those steps will only ever give you exactly X number of successes. They do not give you at least X or less than X or greater than X. It's just going to be exactly X. So keep that in mind for these. So let's say that a survey found that 62% of women believe that there's a link between video games and behavior. Let's say that you randomly select 4 and ask them, whether yes, they believe there's a link, or no, they believe there's not a link. So there's only 2 outcomes, yes or no, success and failure. So the number of trials here is going to be 4. Probability of success P is going to be 0.62. And the random variable x, the number of successes, can be any number between 0 and 4. So we're going to find the probability that for number 1, exactly 2 of them responded yes. So for this first one, it is pretty straightforward. You're finding the probability that exactly 2 of them said yes. So x is going to be equal to 2. So you're going to use that binom-PDF option, where the number of trials n is 4. Probability of success p as a decimal is 0.62. And the number of successes x is going to be 2. So when you do that, you get 0.3 repeating, so about 1/3. So number 1 was pretty straightforward. For number 2, we're finding the probability that at least 2 of them responded yes. You might remember from a couple videos ago that the words at least in math translate to greater than or equal to. So we are finding the probability that the number of successes is greater than or equal to 2. You are going to be using the binomial probabilities on a graphing calculator, but you're going to have to do a couple of them because we're not finding the probability of exactly 2 successes. We're finding the probability of greater than or equal to 2 successes. So since there's only 4 participants, we're going to have to do a couple of different binomial probabilities. We're going to find the probability of exactly 2 successes. Then we're going to add to it the probability of exactly 3 successes. And then add to that the probability of exactly 4 successes. So yes, you're going to have to do this multiple times. You can do the second enter feature to just replace that last number 2 with 3 and then 4. So by the time you have finished finding each of those and then adding all of those together, you should get a probability of 0.843. So yes, you can still use a graphing calculator, but you did have to find each of those probabilities individually and then add them all together. So then for number 3, we're going to find the probability that fewer than 2 of them responded yes. Fewer than is also known as less than. So we are finding the probability that the number of successes x is less than 2. So again, we can use a graphing calculator for this, but we're going to have to find multiple binomial probabilities and then add them together. So fewer than 2 does not mean 2 or fewer, so it's not including 2 here, so it's just meaning less than 2. So the numbers here that are less than 2 are 0, so we're going to find the probability of 0 successes, and we're going to add to it the probability of 1 success. So when you find the probability of 0 successes plus the probability of 1 success, you should get 0.157. You will also notice that if you had just done 1 minus the probability that at least 2 of them responded yes, that you got 0.157. These 2 events here are complements. So these 2 events are complements, which means they are exact opposites. At least 2 is the exact opposite of fewer than 2. So if you just, if you had caught that and you just did 1 minus 0.843 for that third one, that would have absolutely been correct. Now, in these binomial distributions, you can also find their mean and their standard deviation. Now, I will say in the last video, we did do mean and standard deviation of a generic discrete probability distribution. This is going to be the same concept, but because this is a special type of discrete probability distribution, the formulas are different for binomial distributions. So these 2 formulas are the mean and the standard deviation of specifically a binomial distribution. So the mean of that binomial distribution is going to just be n times p, n times probability of success as a decimal. The standard deviation for a binomial distribution, sigma, is going to be the square root of n times p times q. So all of that multiplication does need to go first. So all of that multiplication, you really should have parentheses around that because it's all under the square root. And remember, p and q are always used as decimals or fractions, not percents. So for this next example, let's say that in Pittsburgh, about 56% of the days of the year are cloudy. And we're going to find the mean and the standard deviation for specifically the number of cloudy days during the month of June, which has a total of 30 days. And we're going to interpret those results and determine any potentially unusual values. So success in this case is defined as cloudy. That means failure is defined as not cloudy. So there's only two outcomes. We're either looking at cloudy days or not cloudy days. So the probability of success here, P, is going to be 0.56. N is the total number of days. We're looking at June, which has 30 days, so N is equal to 30. And then we don't really need X because we're just finding the mean and the standard deviation. We do need Q though. Q, which is the probability of failure, is going to be 1 minus the probability of success, which is going to give us 0.44. So let's start with the mean. So the mean of this binomial distribution is going to be N times P, which will give us 30 times 0.56, which will give us 16.8. So what this means is that on average in the month of June, there are 16.8 cloudy days. So then the standard deviation sigma is going to be the square root of n times p times q. So this is going to be the square root of n 30 times p 0.56 times q 0.44. You can do this in a calculator, but you will need parentheses around your square root, and you should get approximately 2.7. So the standard deviation for the month of June is 2.7 cloudy days. So that's the interpretation. So the average number of cloudy days for June is 16.8 days with a standard deviation of 2.7 days. Now, what we're going to do is we're going to determine any potentially unusual values. So you might remember when we did the empirical rule and those symmetric and bell-shaped curves, that anything that is either greater than 2 standard deviations above the mean is considered unusual, and anything less than 2 standard deviations below the mean is also considered unusual. So what we're going to do is we're going to find an unusually low number of cloudy days and an unusually high number of cloudy days. So an unusually low number of cloudy days would be the mean minus 2 times the standard deviation. And an unusually high number of cloudy days would be the mean plus 2 times the standard deviation. So this will be 2 standard deviations above the mean. This will be 2 standard deviations below the mean. And those are the kind of benchmarks that will mark unusual values. So anything beyond those or beyond are considered unusual. So the mean, which is 16.8, minus 2 times the standard deviation, 2.7, does give us 11.4. So we can say that 11.4 cloudy days or less is considered unusual. So 11.4 cloudy days or less is considered unusual for the month of June. Now on the flip side, for the unusually high number of cloudy days, that is going to be the mean, which is 16.8, plus 2 times the standard deviation, 2.7, which gives us 22.2. So 22.2 cloudy days or more is considered unusual. So remember, anything beyond 2 standard deviations beyond the mean is considered unusual. So for the low end, it would be 11.4 cloudy days or less is unusual. And then on the high end, it would be 22.2 cloudy days or more is unusual. All right, so that is going to be it for binomial distributions. that is actually also going to be it for chapter 4. So in the next video, we are going to be starting chapter 5, in which we're going to start on covering some continuous probability distributions, the first of which is going to be the normal distribution, which are those symmetric and bell-shaped curves. So thank you all very much for watching, and I will see you guys in the next video.